All right. I don't know of any major announcements that are out there, but any questions on anything we've covered so far? All right. I would whoa, here's another test here. Put this back here with the others. Okay. Let's go from the current slide. All right. I think we talked about this slide last time, or did we? Anyone here that remembers? Yay or nay? I know some of you weren't here. Did we talk about this slide? Yeah, I thought so. Did we talk about the formula that goes with the slide? I don't think so. That's where I had my mark. So, I guess, well, let's see. I think we can do it here. All right. Here is how we calculate the apparent Doppler shifted frequency for sound given by the equation. Now, for those who weren't here, let's do a quick review on this. Okay, sound is a pressure wave. That means that things get pushed together or pulled further apart. Okay? Now, the frequency of the wave, that's how many wave cycles you go through in a given second. Okay? So the closer these are, let's consider these the compressions of this sound. This car is sounding the horn as he's coming closer to the guy here, moving away from the woman there. And as he's pressing on the horn with a constant beep on the horn, constant pressure on the horn, the waves are getting closer and closer together here, meaning it's going up in frequency. Now, sure, it's getting louder as it gets closer, but it's also going up in frequency. So, you know, like that, not that much. Whereas over here, they're getting further and further apart, so the frequency is decreasing, or at least it sounds that way to her. The horn is the same. The horn is the same, okay? But to her, it sounds like it's, you know, it's going down in frequency. Also going down in loudness because it's getting further from her, but that's what the Doppler effect is. As the car moves to the left, observer A in front of the car hears the car horn at a higher pitch than the driver who is with the car. He hears the pitch that it's actually doing. Observer B hears a lower pitch than the driver because the wave fronts are getting further and further apart. So here is the formula that relates those. Okay, I'll first put down what the character is. The frequency of the horn is F. That's the fixed frequency of the horn. That has not changed. Now, what this guy hears is F prime. That's what he hears. Okay? And what she hears is F prime. Okay? Now, the formula is the same. I'll put the F prime here and F prime here. This is F prime A, F prime B. This is what she's hearing, but it's not actually what the car is sounding. Okay. V is the velocity of the sound. Now, we talked about how you adjust the velocity of sound depending on temperature. We did that last time. If you didn't watch the video, you can go back, read it in the book, or watch the video and see how to do that. Okay, that's the velocity of sound, okay, at a given temperature, okay? Now, the only new thing here, this is the velocity of the source. In fact, that's how fast or slow the source is moving, okay? Now, for this guy over here, who's in front of it, that the waves are getting compressed, his apparent frequency, the Doppler shifted frequency, is F times the velocity of sound in air, that's where he is, in air, divided by the velocity of sound in air. Now, for him, it's a minus Vs. Why minus Vs? The car is getting closer to him. So the denominator is getting smaller. Okay? Guess what? The source is always faster than the velocity of sound. I mean, the velocity of sound is always faster than the source. That car can't move at the speed of sound. Now, airplane might be able to, but the car can't. So V minus Vs, that makes the denominator smaller, which makes his frequency higher. Over here for her, the apparent frequency, the Doppler shifted frequency for her, is the velocity, the frequency of the horn, that's fixed, times velocity of the speed of sound, that's fixed for this temperature, but now it's V plus Vs because the horn, the source is moving away from her, not toward her, so the distance is getting greater. So it's V plus S. That makes the denominator larger, making the apparent frequency lower. So that's why it's going down on frequency for her. Now the book just listed F prime is equal to F times V plus over V plus or minus Vs, depending on if you're in front of the sound that the waves are getting packed together, then you use the minus sign. When you're behind it and the waves are getting further apart, then you use the plus sign. Okay? Does that make sense? We'll do some examples with that, and that's what's coming up next, example 1. Now, is there room on this page to do it? Let's see if we can. An automobile sounds its horn while passing an observer at 25 meters per second. Okay? So the velocity of the source is 25 meters per second. Okay? The actual horn frequency is 400 hertz. Now they put the dash over the last zero, so this is the frequency of the horn, and that's 400 hertz. Now, hertz, remember, is a 1 over second. It's a per second. Also, it could be written as second to the minus 1. That's what a hertz is. Assume that the speed of sound is 345 meters per second. So this, we're going to assume, is 345 meters per second. Now, if you glance back in the book to that page 436, where they have the formulas for speed of sound, it was 331 at the freezing point of water, 0 degrees Celsius or, 0 degrees Celsius. And then it goes up by about 0.6 of a meter per second for every degree. This has gone up, 14 meters per second. So that's going to be probably at least 20 degrees. So probably around room temperature. You don't need to know that, but just to remind you how we got that. Okay? Now, it says the automobile sounds its horn while passing an observer. The A part of the question says, what is the frequency heard by the observer while the car was approaching? Which formula would we use? The minus in the denominator. So that would be F prime, this is the A part of the problem, F prime is equal to 400 hertz, that's the frequency, times 345 meters per second. Sorry, running into the thing here. Let me move some stuff. Let's get that out of the way, that out of the way. We've already got this. Maybe that'll do enough. Okay. Okay. Divided by 345 meters per second minus the speed of the car, 25 meters per second. Okay? Now, they were very kind to us this time. Everything's in meters per second. If they've given that to the speed of the car in kilometers per hour, we'd have to conversions to make. Right now, we're perfectly fine. So let's see what we've got. Okay? That would be 400 hertz times 345 meters per second. And in the denominator, you just add these two, subtract these two. What would that become? Subtract 25 from 345. Pretty easy. What is it? Help me, help me. 320, is that what you said? 320 meters per second. All right. Pull out your handy-dandy calculators and do the measurements. 400 times 345 divided by 320. Or you could do 345 divided by 320, multiply that by 400. Doesn't matter what order you do them, just do them. Say it again. 431 or 81, what did you say? 31. 431 hertz. Does that make sense? Should the frequency go up when it's coming toward them? Absolutely. Okay? So, the B part says, what is the frequency heard when the car is leaving? Now the car is on the other side of them, getting further away. So what's your formula then? F prime is equal to? Now you're this side. The frequency of the horn is still 400 hertz. Okay? Yeah, I wrote my answer down in hertz. Okay? Times 345, the speed of sound is still the same, meters per second, divided by, what do we do this time? Add the 345 meters per second to 25 meters per second. And that would be 400 hertz times 345 meters per second over what? 345 plus 25. 370 meters per second. Now maybe I didn't say this, I didn't say it before, maybe I should have. Notice here the units on here, meters per second over meter per second, they cancel out. So you're left with hertz, so that's exactly what we had before. What do we have this time? A little louder? Hertz, for sure, but what number? A little louder? 373. 373 hertz. Now that's a pretty big shift from 431 to 373. Definitely notice the change when it passes. Yeah, you know, the frequency changes when it goes by, from being a higher pitch to a lower pitch later. Okay? Does that make sense? They have 431 followed by 373. Excellent. All right, that ends what they're going to do about Doppler. And guess what the physics connection is? Ultrasound. Okay, this is definitely one worth a read. A very good, careful read. Okay, because this will be the kind of stuff hopefully you will be doing. Okay, and it has a lot of pretty interesting stuff in that. All right, and it shows a pregnant woman being ultrasound, which I would assume most of them will be and there's the fetus, the image of the fetus that you get from the ultrasound. Pretty incredible. Okay, problems that you could do, any of the odds 1 through 5 on page 441, and any of the odds 7 through 19 on page 442. Only one example, but plenty of exercises. All right. We next move to the concept of resonance. Okay. And there is absolutely no slide with resonance, so what I'll do is leave this and go to the other slide, the blank slide, and pick up that one. Okay. All right. Now, what they say here, they give you the definition, or at least a description, of what they call the natural frequency of an object. Natural frequency of an object. Such as a tuning fork. Do y'all know what I mean by a tuning fork? Okay, it's usually a metal device that has a metal handle, and then about halfway up it splits and goes two prongs that go up. They're very close to each other, and usually if you strike them on something, you don't have to hit it hard, strike them, you hear it go a very fixed tone. Okay, that's a very specific frequency. Okay, that's the frequency at which it vibrates when struck by another object, like a tuning fork rubber hammer. Okay, the frequency at which it vibrates when struck by an object. Okay, by a different object. Okay, now, any of you guitar players? Violin? Piano? Any kind of musical instrument? I thought somebody was something. None. You've seen someone play a guitar before, right? When you put your finger at a certain fret and pluck the string, it produces a certain sound. They move the fret down, it'll be a higher pitch. Move up further up, a lower pitch. Okay, go to a thinner wire, it'll be a higher pitch. A thicker wire, a lower pitch. Every wire has its natural frequency. Now, before you need to start playing that guitar, it's a good idea to tune the guitar. You probably watch people do it, say before a concert or something like this. They'll be up there plucking strings and listening and twisting the thing that tightens or loosens the string, trying to get it in the right pitch. If they had a tuning fork set for a certain one, and they knew which string and which fret would play that note, they could put their finger on that, hit the, well actually probably pluck the string and then adjust the tension on the spring until they hear the tuning fork start making the noise itself. How does that happen? Resonance. If they're on exactly the same frequency, one object will pick up the vibrations of the other object. Okay? So that's what resonance is. Resonance, okay, occurs when a natural vibration rates of two objects are the same. There was, in the sentence before this, I missed seeing it because it was in italics, not bolded. Another name for that is sympathetic vibration, which is what I was just talking about. When you get that guitar string on exactly the right frequency as that tuning fork, same frequency, then the tuning fork does sympathetic vibration. It starts vibrating with the string. It's not touching. It's the vibrations going through the air make it vibrate. That's how piano tuners tune your piano. They have a series of these, and they set them up and hit the strings until they make it sympathetically vibrate with the tuning fork. Okay? You can use boxes like they show in the text on page 443 that sort of amplify that effect, and you'll hit one tuning fork and have the boxes aimed at each other, the other tuning fork will start vibrating. Now, have you ever watched someone do this, especially if someone has fine crystal? Fill that container partially or totally with water, and then dip your finger in the water and run your finger around the rim, and what do you hear it start doing? Making a very high-pitched, well, usually a high-pitched sound. It will start going and get louder as you do that, okay? What you've done then, you've set, by the amount of water you have in there, a circuit frequency of that crystal. If it's very fine crystal, all those molecules are relatively in the same position to each other, and when you hit the frequency that makes them resonate, you definitely hear that. Do any of you remember sort of a dumb movie, but it was a pretty good movie, called Miss Congeniality? Remember that? That was going to be her talent, the FBI agent's talent in the Miss America or whatever, Miss USA, whatever pageant it was playing the wine glasses, okay, filled with different amounts of water, and she was going to play a tune on it until the other contestants drank the water, and now they were all out of tune. So she came up with a new one. But that was this very concept here, making the resonant frequency. It doesn't just have to work with sound. Resonance you use in all sorts of things. Do you think you can push a car? If what? If you were more in shape and didn't have a hurt leg? Well, any of you could, well, certainly you could push on a car, but you may not get it to move. But you can push a car. And here's how, and not just downhill, okay? I wouldn't do it uphill either, but on a flat level surface. What you do, be sure it's not on, the brake isn't on and stuff like this, then it's out of gear and neutral. And then start pushing on the car. And when you give it, feel it give just a little bit, relax. And the car will come back to you, and just when it leaves again, push again. And then relax. And then when it leaves again, push again. And every time you get to push it a little bit further. Why? Because you're pushing the car at its natural frequency. And if you keep doing that, it'll rock more and more and more, and after a while you get it over. Okay? You can push a car. You don't have to be that strong. Okay? Or in great shape. Okay? You can push a car. Lightweight cars preferred. You know, I wouldn't want to do a 16-wheel truck that way. I don't think I could do that, but you can push cars that way. That's an example of resonant frequency. And then I bet you all of you have done this. Push the kid on a swing set. Okay? Do you want to push on that swing when it's coming up to you? No. Okay? That's going to hurt you and probably knock the kid around something. Okay? What you want to do is wait till it reaches its peak and then just give it a little bit of a push. Right as it's leaving and going down, you get on its resonant frequency, and that way with just a little push, they'll say, higher, higher, and you can just push a little bit, and get them to go higher. If they get scared, then push on it when it's coming back at you. You break that cycle and it'll slow down very quickly. So resonant frequency, sympathetic vibrations happen in all sorts of situations, okay? Not just sound, but it does happen in sound. All right. The next topic, and I think I will erase this, is 16.6, simple harmonic motion, okay? Okay. Simple harmonic motion. Type of linear motion okay, a type of linear motion in which the acceleration, remember that from a few chapters ago? The time rate of change of velocity, okay, the acceleration of an object is proportional to, here's a symbol for is proportional to, not quite the same as equal to, but it's proportional to, directly proportional to its displacement from an equilibrium position. Okay. Is it Emily? Okay. All right, good deal. So we're just missing Jordan, Tiara, and Trish. I believe that's all. Okay. All right. Now, let's give sort of an example of this. That's sort of a technical sounding definition. Simple harmonic motion, type of linear motion in which the acceleration of an object is proportional to its displacement from an equilibrium position. Now, if its acceleration is proportional to that, what is also related to acceleration? You sec off net force. Force equal ma. If the acceleration is proportional, so is the net force, because net force is proportional to acceleration. Okay? So the forces. So let's think of an object like a spring. Let me have the spring dangling here. You can put a mass on it if you want to, and that may stretch the spring a little bit. But it's dangling there. When it stops dangling and just hangs there, that's its equilibrium position. Okay. Now, if I were to pull down on that object, the spring's going to be pulling up on it, right? Okay. That pull is a force. Force is related to acceleration, and the more I pull, the stronger it pulls back. So you see the type of linear motion in which the acceleration of an object is proportional to its displacement from the equilibrium position. The further I get from the equilibrium position, the more it's pulling back. Or I could try to compress that spring, and now it's pushing against me, okay? The more I compress, the harder it pushes against me. That will result in simple harmonic motion. Because when I release it from down here, what does it do? It starts going up and down and up and down and up and down like this. Like your car does if your shocks are not good, okay? Up and down like this. Why is that? Because when it's down here, it has the maximum force or acceleration upward. And when it gets equilibrium position, the acceleration is zero. But guess what? It's already picked up speed here, so now it has to compress the spring to start slowing it down. until it reaches up here, and then it goes up and down, because the acceleration is proportional to how far it is from the equilibrium position. Okay? That's simple harmonic motion. One example of it. There are many others, but that's probably the most simple. Okay? Now, and that's the one they give in the book on figure 1626 on page 444. Okay? Now, I hope some of these words will sound similar to you from what things you've heard before. The displacement of an object in simple harmonic motion is its distance from equilibrium or rest position. So, displacement, okay, of an object is in simple harmonic motion, and I'm going to shorten that, SHM, simple harmonic motion, is the distance from its equilibrium position. Equilibrium position. Okay, that worked out well. Now, another name for equilibrium position is rest position. When you leave it alone and it's at rest, that's where it hangs. Okay. Now, hopefully you remember this word, amplitude. We talked about the amplitude of a wave, remember? The amplitude of the vibration is the maximum displacement. Okay? Okay? Of the object. Okay? So let's say you had that spring and it was going up and down like this. The maximum goes up above or below, and they're going to be the same. That's the amplitude. Okay? Now, this hopefully will sound familiar. What is the period? Remember what period was defined as before? Time. It's the time it takes to make, just like it was before, one complete cycle. Okay, let's see what we mean by that. Let's say that we stretch that spring down to here. That's going to be its amplitude, maximum from the equilibrium position. We release it. So it goes going up. It doesn't stop at equilibrium position. There it's not being accelerated anymore, but it's already got speed, so it's going to keep going until it goes up here. Also the amplitude up here, and then finally the spring is pushing back enough so it moves it back. So what is the period? It's the time from down here, up there, and back down again. Okay? That's one cycle. Now, if you did it this way, you had it there, it's at rest, at its equilibrium position, but you thump it. Okay? What you're doing then is giving it initial velocity at the equilibrium position, so it's going to go up. Now, it's not one period when it comes back down here. It has to go all the way to the bottom and back up again, so it's not just at the same position, but going in the same direction. That's the period. The time for it to make one complete cycle. One complete cycle is when it's at the same position, going in the same direction. Not just at the same position, but going at the same direction. So that's frequency. That's period. And guess what the last term is? I almost let it slip. What is related to period? Frequency. And how is frequency related to period? It's the reciprocal. The number of complete vibrations per unit time. Just like we did before, and nothing has changed. These words are the same. if you think about how it mentions period here, the time it takes for one complete cycle, the frequency is the number of cycles per unit time. One is the reciprocal of the other. Okay? If it's a really long frequency thing, a large period, that's going to be a very small period frequency. But a very short period is going to be a very high frequency. Okay, so if it's a short period, very short time period, we usually measure frequency. Very long time period, frequency would be very low, so we might refer to that in terms of how long the period is. Okay. Now, one way to look at this simple harmonic motion, even though our definition was type of linear motion, it's quite often represented well by things moving in a circle. And that's what the next slide is going to show. A good old Ferris wheel. Okay. Now, the Ferris wheel doesn't necessarily follow simple harmonic motion, but it really is closely related. Here's what follows simple harmonic motion. Let's say the sun is directly overhead, and you're the only person on the Ferris wheel, okay? Or your friend is, or someone is. And what you're doing is watching her go around and around, but you're getting dizzy. So what you do, the sun is really bright, it's the only one on there, so you start watching her shadow down here. Right there, the shadow's here. As she moves up, the shadow comes over here, 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 and then at this point it stops and goes back here, 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 and then stops and goes back here. Guess what? The shadow is going at simple harmonic motion from this point to this point. Here's the equilibrium position, maximum distance from that, displacement from that, the amplitude. The time it takes to go from here to there and back there again, the period. The frequency is how many times it does that in a given time period. That represents simple harmonic motion. And a lot of things that are sort of circular in appearance actually follow simple harmonic motion pretty well, like the shadow from this. Think about daylight hours and darkness hours. That is pretty much simple harmonic motion. We're spinning around this, rotating, and that gives us night and day, and that gives us simple harmonic motion. Even though it's a circular motion, we get maximum darkness, maximum light, all that follows a simple harmonic motion. Often the way to describe this is with a sine curve or a cosine curve. And equilibrium position would be the middle of that. The maximum up or down would be the amplitude. The time it takes to complete one cycle, the period. And the frequency 1 over that. All right. Let's see if we have that. Whoa, no we don't. This is figure 627. Figure 1628 is what I was just trying to describe there. And let me get my pen back. This is also called sinusoidal motion. It goes up and down and up and down and up and down. If it's reaching the same magnitude above and below every time, that's the amplitude. And how long it takes to go from one to another, that's the period. And the frequency is how many periods it does in a given time period. Another example of this is, and this seems to be circular, and it is in some sense, is what they call a pendulum. Okay? A pendulum is something that moves about a fixed point here, and it moves back and forth in this kind of motion. Okay? Think grandfather's clock, grandmother's clock, something like that, and that is simple harmonic motion as well. Okay? So a pendulum, let's go to a new page because there's not enough room to write on this one. And that's the last slide in this section anyway, in this chapter anyway. So let's go back to this one. And get my pen back. All right. So a pendulum, okay, is an object suspended so that it swings back and forth about a pivot. That would be that point at the top that it swings from. Okay? Now, I happen to see in the book they didn't do it again, but remember, period is represented by capital T frequency, by little f, and period is 1 over frequency. Frequency is 1 over period. Okay. Little side note there because we're going to be using that later. Now, here's a few things that may be a little surprising about the pendulum. And these three basic properties were discovered by good old Galileo way back. What was it, 14 or 1500, somewhere back there. Okay, we've already, I think, mentioned him before. Quite a scientist. Number one, these are characteristics or properties of a pendulum. Its period, this T here, okay, is independent of the mass. Now, wouldn't it seem like if you put a heavier mass on there, that would change the rate of that it swung? It does not. Okay? It does not. The period is independent of the mass. Okay? Now, air resistance is more affected by the shape, size and shape of the bob than by its mass. That's the thing that messes up a pendulum, is air resistance. Number two, the period is independent of the amplitude. Now, wait a minute. It seems like if you started that grandfather clock, if you raised it too high and started back and forth, it would get off time. It doesn't, okay? In general, it doesn't, okay? Because it's independent of the amplitude. So just get it moving, and it should just keep moving at about that same, at the same frequency, okay? Because of the period. Now, that is when the arc is less than 10 degrees. That's why I say most of the time. You don't want to swing it way up here because then you have other things getting in the way. And then number three, subject to these conditions, okay, this is the arc less than 10 degrees and things like that. Here is the formula for period. Period is 2 pi. 2 pi. Pi is an irrational number, 3.14159, blah, 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 blah. It goes on forever and ever and ever. Never repeating digits, never repeating patterns of digits. Irrational number, okay? 2 pi is the factor by which you multiply the radius of a circle to give the circumference of the circle. Okay? Pretty amazing how much pi has to do with circular things, well, it has to do with this too. Okay? 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity. The length of the pendulum divided by acceleration due to gravity. Now, early in our marriage, I think it was one Christmas, my wife's parents gave us a grandmother clock, not a grandfather clock, but a nice clock hung on the wall. Pretty wood, nice walnut wood, pretty clock, had nice chimes and all. Could never get it to keep the right time. It always was losing time. So what I did, they had an adjustment on it. You could turn up or screw down the mast at the end. In other words, change the length. That adjusted it, but at the maximum, it still was slow. You could not get it any further than that, so it was slow. So it was more a nice piece of wall art than a good timepiece. Okay. So anyway, this is the formula for the period of a pendulum. Okay? And what you want, generally, for a clock is that period to be 1 second, 2 seconds, or something like that. So everything is geared for that length. So this is the length of the pendulum. What is G? Does anyone remember what G is? I said it. The acceleration due to G, gravity. Any of you see Wicked? No, never mind, I won't go there. All right. Now, what is the value for G? If your SI units, 9.80 meters per second squared. Good SI units, but if you're U.S. customary, it's 32.2 feet per second squared. If you remember that, we had those before in an earlier chapter. I think the one dealing with forces. Okay. There's a little blurb here called Swing Set Physics. I've already given one example of swinging for resonance, but you can also see a swing often serves as a good pendulum. So let's do example 1, page 446. Find the length in centimeters. Ooh, this time we're looking for L, not period. That's the unknown here. In centimeters of a pendulum with a period. What represents period? Help me. What represents period? What symbol? Time, capital T. The period of 1.50 seconds. Okay, so maybe this one is set up on 3-second intervals. That would work too. We're looking for L. What formula relates the period of a pendulum and its length of its swing? No, it was a long time ago. What was that formula? Like the last slide? Turn back one page. What formula? Help me, somebody. T is equal to 1 over 2 pi. Is that what you said? Or just 2 pi? 2 pi. Okay, sorry. I was doing it, already moving things around. Okay, 2 pi. I can't write. Times the square root of L over G. This time we're looking for L. So again, you can either plug and chug or chug and plug. Which way would you rather do it? solve for L first and then plug in the values, or plug in values and then solve for L? Plug in first? Okay, we can do that. The T is 1.50 seconds is equal to 2 pi, no units associated with pi, times the square root of, L is what we're looking for. What is G? Now, remember they said they wanted this in centimeters. That was a catch there. So what G would we use? Second? Which G? You have the SIG and the U.S. customary G. Yes, you would use 9.80, but what's that measured in? Meters per second squared. Now here's where we have a dilemma. We can go on and solve this for L. It's going to come out in meters. Or we could change this right here and get it in centimeters per second squared. Which would you rather do? First change it to centimeters per second squared, or solve for L, come out in meters, and then change that to centimeters. You'll have to do the conversion one place or the other. You want to do it now or do it later? Later? All right, put off until, okay, all right. So how would you solve this equation? We're looking for L, so we want to isolate the L. What's the first thing we got to do? Well, let's first get rid of this 2 pi. How do we do that? Divide by 2 pi. Divide both sides by 2 pi. Okay, done here. Now, what you reckon the next thing we're going to do? How do we undo a square root? Square both sides. So we'll square this, and when we square this, we basically lose the square root symbol. And then, one more thing to do before we isolate the L, and what's that? This thing in the denominator, how do we get rid of it? Multiply by 9.80 meters per second squared. Multiply by 9.80 meters per second squared. Okay? So now these go away. Okay? And that would give us L is equal to 9.80 meters per second squared times 1.50 second over 2 pi, but you're going to square that. Now notice what happens to your units. 2 pi has no units, but this does. When you square this, you're going to get second squared, and down here you get second squared. You're going to wind up with meters, which is exactly a good unit for length. So pull out your handy-dandy calculators and do 9.8 times 1.5 squared. Now I happen to know what that is, so I'll go write it down for you. 9.80, and this is going to be meters is all that's left here. And 1.5 squared is 2.25. Check that and see. Divided by 4 times pi squared. I squared the 2, but also have to square the pi. Now, do you have calculators with a pi key on them? You do. Good. So what you'll do is 9.8 times 2.25 divided by 4 and divide that by pi squared. You enter the pi, then square it, and then press equal. What do you get? Anybody? 9.8 times 2.25 divided by 4 and then divide by pi squared.
I don't think I did it right.
What's that?
I don't think I did it right.
What do you get?
2.34.
Okay. Yeah, I think probably it comes from that squaring the pi. Let me watch you do that. I'm moving slowly. Okay. 9.8. You don't need to do the 0. Times 2.25 divided by first 4, then divide again by, where's your 5? Okay, and then square it. So your square key is this one right here. It's the other x squared. And then it equals. Oh, what do you get?
0.5585.
Okay, hold on just a minute. Let me sit down and write that. 0.5585. That's enough. In fact, that's more than enough. We've only got 3 significant digits there, 3 there. Pi is to as many places as you want, so we're 2 as many places as you want. So actually, we only got 3. So let's round this, and this will be meters now. So we got 0.559 meters. Okay? But we want this in centimeters. So how do we make that conversion? Blank blank equal blank centimeters. Always put units in their place. What unit goes where? Between meters and centimeters. One goes on top, one goes on bottom. What goes where? Meters on the bottom, centimeters on the top. Now you answer the question, how many centimeters in a meter or meters in a centimeter? Anyone know? How many cents in a dollar? 100. So there's 100 centimeters in 1 meter, right? Okay. And when you multiply by a power of 10, you just move the decimal 2 places. So this would be 55.9 centimeters. Almost 56 centimeters. And that's what they got in the book. So that finishes 16.6. Again, only one example, but they give you 14 problems. So you can do any of the odds. I would do either 1 or 2, either 3 or 4, either 5 or 6. No, yeah, 5 or 6. Either 7 or 8, and then any of the odds, 11 or either 11 or 13. Okay? And that finishes Chapter 16. There is a good glossary here, quite a few words in it. Covers 1 full page and a couple at the top of the next page. Several formulas, well worth your keeping up with those. And a few review questions that basically test your concepts. But the review problems, those are quite good. And I think the odds are in the back, so any of the odds, 1 through 17. Yeah, 1 through 17. Okay. Now, since we finished Chapter 16, let me give you the test for Chapter 16. And again, there's a couple corrections. If you think the PowerPoint shows are pretty lame, the test bank is pretty poor too. So here is the test, Chapter 16 test. Again, you can have up to 2 weeks to work on it. I mean, it can take longer if you need it, but try to get it in 2 weeks. That gives you 1 week to ask questions. Ready? What? Either what? Okay. And we've got, I think, 1 for each. Few people missing. 1, 2, 3. I think that's right. Jordan, Tiara, and Trish. Yeah. All right, here are the corrections. Sorry about this. Number 8. A train traveling at a speed of 80 miles per hour approaches an observer at a station and sounds a whistle. What frequency will be heard by the observer? Assume that the sound velocity in air is 1,090 feet per second. Okay? You notice anything that's missing? The frequency of the whistle. You can't do the problem without it. So I had to do it backwards and come up with, and I believe it comes out to 585 hertz is the frequency of the whistle. You need to figure out what is the frequency heard by the observer as that whistle's coming close. Now, is there anything else you notice about that problem that might be a little bit of an issue? The speed of the train is given in miles per hour, but the speed of sound in air is given in feet per second. So you've got to do one of our conversions to get the miles per hour to feet per second, just like we've done them in the past. And then if it wasn't bad enough for number 8 to be missing it, number 9 says a car is traveling away from you at 70 miles per hour. Have they done the same thing? The car horn produces a sound at a frequency of, and they even put the frequency of in there and then left it off. Okay? I don't know how this got by. That should be 5,000 hertz. And it says, what frequency do you hear? Okay. Now there's something else missing in that problem. Okay? They don't give you the sound velocity in air, so use the same one you used before, 1090. But then, again, just like you did before, you're going to need to convert your 70 miles per hour to feet per second. Right? But they didn't give you enough to do. Missing the sound velocity, you can use the one they gave you before. But in neither problem did they give you the whistle frequency nor the car horn frequency. And frankly, I found those pretty amazing. Whistles I usually picture as being higher frequency than car horns. They have this whistle at a very low frequency and the car horn at a very high frequency. But that's how the problem works, so we'll go with that. Any questions on that? Okay. Whoa. Somebody's really anxious to get out of here. Okay. Now, we've got more time, so if you have to go, I understand. Okay. Just because I gave the test doesn't mean it's the end of class, okay? But we can go on from there. All right. Chapter 17. In fact, the next several chapters will be one after another, no skipping around like we did before. But it's a completely different subject. Chapter 17 is basic electricity. Okay? Now, if you recall, at the very first of the term, I told you which sections we're going to be talking about. And the sections we're going to use is mostly 3, 4, 5, 7, 8, and 9. But you can't really do 7, 8, and 9 unless you do 6. So 3, 4, 5, 6, 7, 8, and 9. Okay? Because you got to know Ohm's law to do 7 through 9. They didn't mention Ohm's law in the thing, but you got to have it. Now, before we launch into 17.3, though, I wanted to at least cover the basic definitions in 17.1. So we will do a little in 17.1. Okay? Let's go to a clean slide here. I also need to, that's not what I wanted. Actually, I do sort of want that, but I want to change my other slide. That's chapter 16. We need to do chapter 17. Okay. All right. Let's start from that slide. We'll probably have to go back to our blank page. Chapter 17, basic electricity. Okay? Now, This is how electricity gets its features. Now these are illustrations. They're not necessarily realistic illustrations, but they're just illustrations to serve a purpose. All right? Now it's showing here a normal atom. Okay. Here's what's wrong with this picture. The nucleus, this is called the nucleus of the atom. If that was the nucleus, it would be incredibly tiny. You wouldn't even be able to see it on the page hardly. It would be one little pixel there or something like that. But it is incredibly dense. Just about the entire mass of that atom is in that nucleus. Now flying around here are these electrons. Oh, and in the nucleus we have protons, which are positively charged, neutrons, which have no charge, and electrons out here that are negatively charged. These electrons have almost no mass. I mean, they have a little bit, but way, way, way less than what a proton or a neutron has. Okay? So all the mass is concentrated in the nucleus, but only 3 positive charges, the way it's shown here, 3 positive charges. And then on the outside, taking up almost the entire volume of that atom, are 3 little electrons that have almost no mass, but have the same charge as the big old protons do. Okay? So that's your setup. Now, if this was indeed an atom with 3 protons and 3 electrons, that would be lithium. But you don't need to know that. They're just using a representative sample. Okay? Now, it's not showing any neutrons. There would be probably at least 3 neutrons in there too. But they don't have any charge, so they're not showing it. Now, and this does happen. This is very realistic. This lithium is real easy to lose 1 electron. And if it does, it becomes not a normal atom anymore, it becomes an ion, a lithium ion. Now, they don't say the word here, but that's what it is, an ION. Okay? Because it lost an electron, it now has a +1 charge. And lithium quite often will lose an electron and have a +1 charge. In fact, lithium reacts with lots and lots of things. You very seldom, if ever, will find pure lithium by itself. It's always connected with something else. Okay. Now, the next one is not realistic. It's just done to represent something. What if that lithium gained an electron? Didn't lose one, but gained one. Now it would be a negatively charged ion. This would be a positive charged ion because it has more protons than electrons. This would be a negatively charged atom because it has more electrons than protons. Still lithium. That's lithium atom, a positive lithium ion, and if you ever had it, which you don't, that would be a negative lithium ion. Okay? So all the charges reside in the protons and electrons. You don't change the numbers of protons. They're in that nucleus, they're fixed. What you change is your electrons. Either losing electrons, becoming positively charged, gaining electrons, becoming negatively charged. Okay? So that's the source of your charges are your electron exchanges. That's it. You don't change. To change protons, you have to have a nuclear reaction. We don't want that. Okay? What you have in normal chemistry is movement of electrons. Okay. Now, I didn't write all those terms down. Electrons are negatively charged particles, very, very low mass, but take up almost the entire volume of the atom. Proton, positively charged, enormous amount of mass, but located in a tiny, tiny, tiny little nucleus. And neutrons have actually a little bit more mass than the proton, but basically the same, and has absolutely no charge at all. All right. Now, that's all we need, I think, from 17.1. We're going to skip 17.2 altogether and go to 17.3. Now, 17.1 or 17.2 talked about these electroscopes. And I've taken class time talking about those before, and then we don't get time to do the stuff we really need. So we're not going to deal much with this. You can read in the book if you want to, but you're only going to be responsible for things starting with Coulomb's law. Okay? This is more electroscopes. More electroscopes. Van de Graaff generator. Okay, you may have seen those operate before. Now we're getting to what we're going to cover here. But this jumps way ahead. In fact, this is in pages away, 17.5. So don't sweat this yet. Let's go back to our blank slide. Okay. Coulomb's law, 17.3. This is really where we'll be beginning chapter 17. Now remember, what's the charge on a proton? It's a positive charge. We denote that by the symbol E+. Now, usually E stands for electron, right? But the charge on an electron is identically the same as the charge on a proton, except for the sign. So an E+ would mean a proton, and E- would be an electron, because it's a negative charge. Same value, only different signs. Okay? Now, this represents the charge of a proton. I'll go and put it P+, because I don't like to write it out. And this is the charge on an electron, which I call E-, which is E-. Okay. In the study of electricity, a much larger unit of charge is required because these little charges, they are incredibly tiny. The charge on a single electron or charge on a single proton, so incredibly tiny, we don't have any equipment to measure them, really. We can measure the difference of things, but we can't measure that by itself. Okay? So, in the study of electricity, a much larger unit of charge is required, and it's called a coulomb. That's the unit of charge. The SI unit of charge is a coulomb. Its symbol is capital C for coulomb. Guess why it's a capital C? Named after someone. Charles Coulomb, a French physicist he's talked about over there. I'm sorry. Yeah, he was born in France. What I meant to point out, let me go, I haven't. Yuck. Remember when I showed the picture of the kids with the Van de Graaff generator? Where do you think Van de Graaff came from? Hearing the name, I would have said Holland, the Netherlands, because that's a very Dutch-sounding name. You know where he came from? Tuscaloosa, Alabama. He was a physicist born in Tuscaloosa, Alabama. He invented this Van de Graaff machine. Now, I don't know if he went to school at University of Alabama. That would really be great if he did. I have a feeling he went elsewhere, but I don't know. Born in Tuscaloosa, Alabama. Too bad we don't have more time to do with that. But Charles Coulomb was born in France. Okay? Pioneered research in electricity and magnetism. The unit for measuring electricity, Coulomb, is named after him. Okay, so this measurement of this unit of charge gives the E+ for a proton, the charge on a proton, is positive, because it's a positive charge, 1.60 times 10 to the minus 19 coulombs. Now, coulomb we can measure. With most of our equipment, yeah, we can measure a coulomb of charge. But you see, a single electron or proton charge is so incredibly tiny That would be 0.000000000000000 19 zeros before you get to 0.160. It's an incredibly small amount of charge. So that's why we measure coulombs but refer to the other. Now, charge on electron, E minus, that would be minus 1.60 times 10 to the minus 19 coulombs. It's just the same charge as on a proton, only negative in charge. Okay. How many electrons would it take to make 1 coulomb of charge? Well, you take this number and reciprocate it, and what you get is 6.25, whereas this is an incredibly tiny number. This will be an amazingly large number, times 10 to the positive 18 electrons. And I'm going to put E minus because that sounds, I use that for electron. That would be 6,250, 000, 000, 5 more sets of 3 zeros up to your 6.250. An enormously large number. I don't even know what that would be. 10 to the third is thousands, 10 to the sixth is million, 10 to the ninth is billion, 10 to the 12th is trillion. This is a million trillion. I mean, it's an enormously large number of electrons to make 1.00 coulomb of charge. So we're dealing with incredibly large numbers of electrons to make our charge change. Now, the symbol for charge is Q. The unit for charge is coulomb, but the symbol, the parameter for that is Q. This represents charge. Okay, that's what that stands for. Now, charge, like so many other things, obeys what we call the inverse square law. Okay? If we had 1 coulomb of charge right here, right there, and we went over here to measure it, and it only measured half a coulomb. It's 1 coulomb of charge, but the charge density, when you got here, say, was half what it was here. When you doubled the density, now you'd have a quarter of it. Tripled it, 1/9. That's called the inverse square law. I think we talked about that before. It comes from the fact that things relate by the square of the density, square of the distance, not the distance itself. It's an inverse square law. So putting that together, we get what we call Coulomb's law of electrostatics. Can I write it on this page? Maybe not. Let me go to a clean page. Okay? Here is Coulomb's law. Quite often don't say of electrostatics, but that's what it is. The force between two point charges, Q1 and Q2, they don't have to be the same charges, 2 point charges, Q1 and Q2, is directly proportional to, remember we had that before, I used the symbol that for proportional to, the product of their magnitudes okay, and inversely proportional to, I'm going to use proportional to again, the square of the distance separating them. Okay, pretty lousy writing. Okay, and that distance we usually call r. Think of a radius. So here's how we write Coulomb's law of electrostatics, or just Coulomb's law. The force between two charged bodies is proportional to, these proportionalities, you can change that to an equal sign if you put a proportionality constant. So I'm going to put equal K. That's your proportionality constant. The product of the charges, Q1 times Q2, divided by the distance squared, radius squared, r squared. Now, that K is a constant. It's a constant of nature. Anything electrical is going to obey that. And that constant happens to be, this K, is 9.00, I can't write. Late in the day, I'm just running out of juice here. 9.00 times 10 to the 9th, positive 9, Newton meter squared per Coulomb squared. Now, seems like weird numbers for our units there, but here's why. The force is measured in newtons. That's what you would measure SI unit for newtons, okay? But you need to have Coulomb squared here to cancel out, because this charge is in Coulomb, that charge in Coulomb, so that cancels out the Coulomb squared. This down here is in meters, the radius in meters, so that, since it's squared, the meters squared cancel out, and that gives you newtons on the other side. So sure enough, that's the right units. Okay? Now, remember, forces are vector quantities, they have directions. And I wanted to point out one word they sort of snuck in here, and that's their magnitudes. Directly proportional to the product of the magnitudes. It doesn't matter what sign those charges are. One can be positive, one can be negative, they could both be positive, they could both be negative. Doesn't matter, the force is this. What the signs of those charges do, that's why the magnitudes is what we deal with. What the signs tell you is whether it's a repulsive force or an attractive force. What's the rule for that? Like charges, like two positive charges, repel each other. Two negative charges repel each other. But a positive and a negative attract each other. So the force of attraction or repulsion, don't matter. Don't get the signs crossed up in here. Just use the magnitude. That's the force. Then determine whether it's repulsion or attraction based on the signs. Don't let the signs confuse you. You separate them and deal with them. Okay? So let's do example 1. Any questions before we do? They have an interesting little try this activity here. You can do it if you want to. I have actually done it. I've seen it done. But it says turn on the faucet so only a very thin stream of water comes out of the tap. It says charge a plastic rod, a latex balloon, or a plastic comb by rubbing it with a piece of wool or fur. Now, if you have a comb, and now it requires your hair to be pretty clean and not much humidity. And in the South, we don't have days that you don't have much humidity. But if you did have that, and you combed your hair real rapidly, then you charge the comb. And what you could do is when that water is just beyond dripping down, just a little stream of water, hold that charged comb near the water and see what happens. I think we'll see it pulls to the comb. That's electrostatic attraction. Okay? If that doesn't work, you can use little pieces of paper. If that doesn't work, try something else. Take wool or fur and rub plastic, latex, glass, something with that. Okay. So let's do example 1. I'll go to a clean page here. Okay. two charges, each with magnitude, they say magnitude and give it positive, it's okay. Two charges, each with magnitude of 6.5 microcoulombs. So you have Q1, 6.50 microcoulombs, and charge Q2 is 6.50 microcoulombs. Now, what in the world does that micro stand for? Anyone remember? Metric prefix, micro. Milli is 10 to the minus 3. Micro is 10 to the minus 6. So this would be 6.50 times 10 to the minus 6 coulombs, and this would be 6.50 times 10 to the minus 6 coulombs. Okay? It says two charges, each with magnitude of 6.50 microcoulombs, separated by a distance of, what's your distance? The book uses R. R is equal to 0.200 centimeters. Boy, are they ever making it rough today. All right? Centimeters is not the SI unit for distance. What is? Lose the centi, and what you get? Meters. So what we have to do is convert this to meters, just like we converted microcoulombs to coulombs. Micro means 10 to the minus 6. Now you can do the same thing here, but here's what I suggest. Let's do our train track, okay? And we want to get to meters. So what unit goes where? One goes on top, one goes on bottom. Which goes where? Tell me. Something on top, something on bottom, between meters and centimeters. Centimeter, no, if you put centimeters on top, you get centimeters squared per meter. That's, yeah. The centimeters have to go down here so they can cancel out, and meters on top. Oh, I put them on the wrong block. Sorry. That was my number block, okay? I want my unit block, okay? Meters on top, centimeters on bottom. Now, what unit goes with what? What number goes with what? How many meters in a centimeter or centimeters in a meter? 100 which way? 100 centimeters makes 1 meter exactly. So what happens here, you move your decimal 2 more places to the left. So if you're using scientific notation, if you do it just this way, it would be 0.00, that's the 2 from here, 200. Woo, a lot of zeros. So if you want to use scientific notation, move this 3 units to the right, and that's 2.00 times 10 to the minus 3 meters. That's actually probably the easiest way to express it. You can use 0.00200 meters, but this would be probably a little easier to work with. All right? Find the force of repulsion between them. So you're looking for F. Now, they say repulsion because they said they were both positive charges. Okay, so it's going to be repelling. What force would that be? Whose law do we use? Coulomb's law, and how does that go? Okay, K, F equal K Q1 times Q2 divided by R squared. Okay, your K, remember, was 9.00 times 10 to the 9th Newton meter squared per Coulomb squared times 6.50 times 10 to the minus 6 coulombs times 6.50 times 10 to the minus 6 coulombs divided by 2.00 times 10 to the minus 3 meters, but you got to square it. Wear out your calculators, aren't you? Let's deal with the units first. Notice the coulomb squared cancels this coulomb and that coulomb. The meter squared cancels that meter squared. So sure enough, we're left with newtons. That's a very good unit for force. So let's deal with our numbers then. All right. Hopefully you have calculators. So here's what you punch in. Remember how to do scientific notation? EE or EXP? Okay. So 9, you don't have to put 0, 0. EE or EXP, 9. That's what that one is. 9 EE or EXP, 9. Times 6.5, you don't have to put the 0 down if you don't want to. EE or EXP, negative 6. Okay, now remember when you do a negative 6, use that negative in parentheses. Don't use the minus sign. The 1 in parentheses. Okay? Times 6.5, EE or EXP, negative 6 again. Then you do your dividing by 2. You don't have to put the 0.00. EE or EXP, negative 3. Okay? But then you're going to square it. And then hit equal. Okay, if you want me to watch you do that, I'll be glad to. See what number you get. Anyone get a number? Anyone? Oh, okay. I'll be glad to talk you through it again. You want me to? You got it? What you get? Okay. Want me to watch you do it? Did you get 9.51? What you do. Okay, yeah, you don't get times though. Okay. Oh. So start at 9, and then EE or EXP. Yeah, that's the EE. So it's second EE. Okay, you already did that second EE. Okay, and then 9. Okay, that's the exponent. Away. 9. Yeah, that's it. Times 6.5. Okay. Negative 6, right? Times 6.5. EE, right? Negative 6. Okay, 2 EE, negative 3, and then square that number. Okay. Actually, yeah, put that, wait. Right before the 2, open parentheses. I think it lost you 2. 2 EE, negative 3, and close that and square it. Okay, there you go. Let me see you do that a little more slowly this time. Okay. Take a look. Oh, okay, you never hit the square.
Oh.
I don't see why it's giving you an error there, because it looks like you did everything correctly. Now, what I don't know is what this normal float, auto, that kind of stuff is. If you're in the wrong mode there, that may be the issue, but I don't see why these numbers are typed in exactly correctly. You were using this minus here, not that, right? Yeah. Beats me. Some of these calculators are smarter than I am, so I can't understand why they. Okay. What's that?
I said I probably figured it out. I said I probably figured it out.
Okay. You want to try it on your phone? Let's see if we can get it there. Let me see if there will be scientific notation. Yeah, there's an EEP there. Okay, so it's 9 EE 9. Okay, yeah, there it is. Yeah. Times 6.5 EE, and then let's see where your negative 6. Oh, yeah, okay. You do the 6 first, and then change sign. Okay, times, okay, 6.5, and then EE, your 6, change sign, okay, divided by, okay, 2, EE, 3, and negative, and then, oh, we forgot to do your parentheses, sorry. That's the thing. I don't know how you back up on this. Okay. I think you have to start at 9. EE 9. Okay, that's correct. Times 6.5. EE 3. Change sign. Times 6. Whoa! I don't think that gave you the right number. Okay, start at 9 EE 9. No. 9 EE 9. Times, yeah, that's right. 6.5 EE 6. Negative. That's right, yeah. Times 6.5 EE 6. Negative. Divided by, open parentheses, okay, 2 EE 3 negative, close parentheses, square. Equal. All right, let's see what we got. Goodness gracious, I'm stiff and sore. All right, read what you got there. 95,000. Second?
95,062.5.
062? 062.5? Okay, and that would be newtons. So to get that in scientific notation would be 9.5. You only got 3 significant digits everywhere, so count 3 digits, 1, 2, 3. Look to the right, that's a 6. So you boost the 0 up to a 1, times 10. Now how many places did you move your decimal? 1, 2, 3, 4. 10 to the 4th newtons. And let's see what we got in the book. 9.51 times 10 to the fourth newtons. Way to go. Okay, that's a lot of newtons. Okay, and microcoulombs, that's not very much charge at all. 0.2 of a centimeter, that's really close. That's a millimeter. A millimeter is about the thickness of a dime. So that's quite a bit of charge, even though it sounds pretty small, pretty close to each other. That's very repulsive. Okay, so that's all we got for 17.3. So do any of the odds 1 through 7. Please do some of those. You'll probably be seeing more like that. Okay. Now we're going to talk about electric fields. Okay. This is 17.4. So I think I'll just clear my slide here. Do you need that any longer? Okay. Now, so far we've discussed electrification due to brushing, blah, blah, blah. We didn't do much of that. In terms of static electricity, an electric field exists where there's an electric force of attraction or repulsion acts on a charge brought into the area. Okay? So that's what an electric field is. Okay? It's an electric force. Think Coulomb's law, electric force. That's what we got from Coulomb's law. Either attraction or repulsion acts on a charge that's brought into it. Brought into its area. Okay. Now here's what we mean by that. Let's say, remember we had this charge here. Whatever it is, have a charge here. Now, if it's just sitting there with a charge, I don't notice it. You don't notice it's just sitting there with a charge. But if I bring a little charge in somewhere from way out, maybe out from the hall somewhere, and bring it in and get it closer and closer to this one, then it's going to start feeling that force. Why does it feel the force? Because of the electric field around this charge. Okay? Now this electric field, if you can imagine, picture it as being lines going out, and the further it is away, the further those lines are from each other, there's not much there. But you get close to it, the lines are real close together. So you feel more force here. So the field is also proportional to distance. Okay? So that's what an electric field is. In terms of static electricity, electric field exists where an electric force acts on some charge brought into its area. Okay? Now, electric fields can be measured using test charges, like that charge you brought in could be called your test charge. Okay, it's usually pretty small, always considered to be positive. Okay, so let's say we brought a very small positive charge. When you kept it out, you brought in a small positive charge. Here's a field here. Now, what do you want? I mean, a charge here. What do you want this to be? Positive or negative? I don't care. Positive. So you bring in a small positive test charge. What is it? Once it starts feeling that, where is it going to be going? Away, because like charges repel each other. So therefore, we say the field is in that direction. If you brought it in over here, it would be in that direction. Over here, it would be down there, okay? It's anything away from that positive charge. However, if this was a negative charge here, and you brought in that small positive test charge, where is it? What is it feeling? Attraction moving to that, so that your field would be toward the charge. So, here's the key. Positive charges, the electric field is always pointing away from it. Negative charges, the electric field is always pointing towards it. Okay? So, you're bringing in a single charge. So, here's what is happening there. Here is the formula we use. the electric field, that's E, is equal to force per unit charge. Okay? Force per unit charge. That unit charge is your test charge. Small positive charge that you bring in. Remember, force is a vector quantity, so is field. Okay? Now, what would be the units for your field? Well, this would be newtons per coulomb. That's 1. Okay? That's the only one to give for now. There are some other charge units we'll use later, maybe, but that would be the one we'll use now for electric fields. Okay? Newtons per coulomb. So, I think, do we have time for example 1, you reckon? Yeah? No? Not really. Okay. We'll begin next time with example 1. I'm sorry? What are we on? This is chapter 17, and we're in section 17.4. Okay? 17.4. All right. Now we started the ninth in 16.4. So we went 16.4 to 17.4. All right. Good deal. We'll see you next week. Have a good weekend. Working on those tests will make it good.